Okay. Hi, everyone. Thank you for coming. Today we will be talking about um, we'll finish talking about the Neuron Python package and then go into the BRIAN2 Python package. So we'll go ahead and get started. Here's the attendance and the pre-assessment. So I'll see if I can get those in the chat real quick. All right. So again, here's our team agenda today. So we'll again do a really quick review of the paper. I'm just going to kind of zoom through that part of it, since we've seen that a lot already. And then we'll do a little quick overview of Neuron, finish up what we were talking about, and then talk about the BRIAN2. We'll see a couple examples of those notebooks, and then that'll be it for today. So again, review the paper. We're looking at the Drosophila flies and their response for the escape and what that latency looks like. Um, so again, that latency is going to get longer as they're getting older, and we see that is related to the gap conductance. And where we're studying that, these two pathways, the jump and the flight pathways. Um, so here we see the two pathways, the TTM and then the DLM1. So again, if we have any questions about that, feel free to stop me. And then again, old versus young, we see that the younger ones have a quicker response, older ones have a slower one, and we see that this response is related to this gap conductance. So that's how we're measuring between old and young flies. So now reviewing the Neuron Python package. Um, so again, the whole purpose of using computational um, neuroscience is so that we can create this biophysical model of the neurons and circuits, um, and that we're basing it off of real anatomical data. And in this paper, they used the Hodgkin-Huxley model. So we'll want to use that version in the BRIAN2 package. And then again, we're basing the old and the young based off this gap junction conductance. Um, and the younger ones have better conductance, and the older ones have worse conductance. All right, so then we saw this is the one that I uploaded later to um, the group chat. So I'll share this real quick in the chat. This is the Neuron notebook. Um, and it just kind of describes what all the different parameters are and how you make them. What's unique about the Neuron one is that it uses these N model files or these .mod files, and that's how you define the ion channels in the neurons. So because of that, it made it a little bit difficult, in my opinion, to run it, or not difficult, but just an extra step that you need to do on your computer. So again, this whole notebook kind of talks about these differences, and they're modeled using these different types of differential equations. And all that a differential equation means is that we have a derivative in there or different types of derivatives to describe the behavior that's going on in the system. So again, it talks a little bit about the Hodgkin-Huxley neuron. And here we see this as well. So this is kind of what the .mod files would look like. I'm not going to go too in depth in this one just because we want to focus more on the BRIAN2. So this is just kind of a review of how they did it or how you could do it using Neuron, which is what the paper used. So we'll just kind of go through this a little bit. So you see they're using different functions. So feel free to look at that, but we're going to go ahead and keep on moving on into BRIAN2. So what is BRIAN2? So it's another Python package that accomplishes the same thing as the Neuron Python package. The only difference is, the syntax with some of the things and how they classify their models and how they do it. So the hope is that if we can recreate the same results using this Python package, that it makes the findings of the paper more robust, which is what you want in science. You want multiple different sources or experiments to come to the same conclusion to make that finding more valid. So the BRIAN2 package, what's different about it is that it's purely Python in the sense that we don't have those .mod files that we need to compile before we run our script. So in a way, it's less steps to implement, but then we just need to specify those in the code. Another good thing is that it enforces dimensionality, meaning that you will have to specify the units. So if you're talking about time, you need to include the unit of time. Otherwise, it might throw in an error because it doesn't know what it's talking about. So in a way, it's good that it enforces that. Otherwise, your code won't work. The cable compartments are straightforward. So how it is describing the neurons or parts of the neurons physically. Um, and then, and it does it in the neuron group. So we'll see that syntax later. And then the gap junctions, it's the syntax of it is formatted in a way that it makes it easier to do the young and the old fly comparison using that gap junction conductance. And then again, since we don't need to compile any of the .mod files, we can run it anywhere, which makes it nice. So comparisons between these two, uh, equations versus infrastructure. So the Neuron Python package has this built-in biophysical machinery. So, you can have sections or segments versus with BRIAN2, you have more control over what you want to do, but the flip side to that is that you'll need to specify everything more, which just means writing out more things. Same thing with the channel definitions. Again, these are compiled in the .mod files. This one you specify out in strings. Um, and again, the neuron has these um, for these spatial morphologies, it has the WSWC files, versus BRIAN2 will have to specify that manually. So more manual work on the BRIAN2 side, but it allows you to tailor it to your experiment, which is nice. So now we'll kind of go through different notebooks to help you get more familiar with BRIAN2. So the first one we have here, I'll go ahead and share it in the chat. So we have that in the chat. And then just make sure when you're running these files that you go ahead and go to File and save a copy in your drive. Um, so this notebook is just kind of focused more on the different ways you can simulate the neurons. So if you want to skip to what we'll be doing in the paper, you'll just go to this Hodgkin-Huxley model. But you can just see the different ways to simulate it and how that changes how the spike looks like. Um, so again, to do it, you would just do each cell individually, or you can come up here and hit run all, and it'll do it for you. Either way, this notebook installs a package, BRIAN2, which we're using. And then they also cloned a repository. Um, and maybe we'll have a workshop on that in the future about accessing GitHub and more specific to our work here. But for now, all you need to know is that it'll just kind of import some scripts that they use, which is nice. Then you import some other things, and we'll get down to the spikes. So you can hear these spikes are very rigid. Um, so maybe that's not the most realistic neuron. You can also see these here. I'll just go down to the Hodgkin-Huxley one. So these are the equations that it uses. Um, and we'll see that. And then H, these are two gates. So sodium channel is gated by two gates, and then the potassium channel by a single gate. So these are representing those gates here. And then this is our voltage. So you'll see here in BRIAN2, we're specifying all of our equations, and we have to do that. It's not anything automatic. And then you can specify all your parameters. And here they create sliders, so if you want to change certain values, you can. And then we see an example of that here. So we can see these spikes look a little bit more realistic. Um, so we'll see this is the membrane potential, spike, spike, um, and this is when you're putting in a current. So this notebook is just helpful to get used to the package, to see how different people code the neurons and how the general structure is. I'm not going to go through everything because you'll have these examples to do, and then we want students to actively try and figure out and really engage with the code to try and replicate the results in the paper. So now, if we look back to the paper, some of the figures that we saw this one earlier. Um, we saw that these are the anatomical numbers that they used for the different types of neurons. Here's the TTM, PSI, and the gap junction conductances. So these values will be important when you're making your models. If you're wondering like, oh, well, what do I set this value to? Just reference back to this table. And then for some of the charts, you'll be varying these numbers. So what we can do is in this notebook, It kind of replicates some of the figures. Um, it gives you ideas of how to represent these same concepts in the paper. We don't have to recreate the figures exactly using the BRIAN2 package, but the ideas need to be similar. So for example, for this one here, panel B, this this notebook recreates it kind of, not using the exact same values and everything, but you get a similar result. So here we can see these different traces of the fly for different regions, TTM, PSI, DLM, and then the voltages in response to stimulation. Um, so here where they like overlaid them all, this is just them represented, not overlaid. So you could do that, or you can overlay it again, um, whatever you prefer. But this script will give you an idea of how to start to represent some of these things. It doesn't do all the figures and not all the figures exactly, because we want students to work on that, but it does give some ideas. So here you're setting your some of your parameters. So again, referencing back to that table earlier, here you're importing and everything, setting your parameters, and then here's where you're gonna set your function. So that's kind of like the structure of how you want to structure your notebook is install everything, set your parameters, do your function for your simulation. And you can see here, each neuron is its own neuron group. So we're setting our function. And you see here how you have to multiply by the units. And then you can run your simulation to get those figures. So running your simulation, and then you can plot those figures. Now, another figure represented here in this notebook is these um, plots. So if you remember with these, on the y-axis we have the gap conductance, the gap junction conductance. So if we remember, around 34 was our old flies, which is represented by this orange shot. And then the younger flies had a higher conductance, around 130-ish, represented by this blue dot. And then here we varied, um, different types of conductance for sodium, um, potassium, and this leak one. So, they're varying this, and we're seeing what has more an effect on this conductance. So we see here that the effect is more with the gap junction conductance, um, meaning that has a larger role than varying this parameter. And these are represented physiological parts of the neuron versus if we looked at the anatomical ones, um, instead of just seeing these horizontal lines, now we're seeing some curves, some more vertical changes, which tell us that when we're vary this parameter, um, we're getting those changes. So, but these plots were kind of confusing. So, um, some of the faculty recommended that you can represent the plots this way. So, And again, this is just an example. This is not the, some of these are not the actual values because we want people to have the chance to do that. So, but here we see that we are, we'll zoom in on one. So again, this is looking at one of the physiological conditions, maybe. Um, and here the axes are switched. So this is your gap junction conductance is on your x-axis now, and then you have your other potassium conductance on the y. So again, around 34 for the old flies, 130 for the younger flies, and then we're seeing, okay, is this change more along the vertical axis or the horizontal axis? So in this one, we see that the change is more across the horizontal than the vertical. In some of these lower regions, we see it's more vertical, but more horizontal overall. So this tells us that varying the gap junction conductance has a larger role than the potassium, which tells us again that the varying the physiological conditions is not going to have much of an effect. Now, if we repeated this with the anatomical parameters, we would probably see this flip and see more of a change along um, the other axis versus this one. So this is another way to represent that, and this code for this notebook helps you with those figures. So it's more about um, replicating this using the parameters for the physiological ones, and then repeating that same process for the anatomical um, parameters. So does anyone have any questions so far about anything? Okay, perfect. So let me put the link in for that notebook real quick. They're also in the group chat, I believe. And then make sure to make a copy yourself. All right, so now we'll review that. So anyone, you can just put a thumbs up or maybe on a scale of 1 to 5 of how you're feeling with coding, um, and just kind of the packages all understanding that the packages all together, the paper, um, and any feedback if you want to text me or anyone on our leadership team about how we could support you. Um, I think we will we will create more resources to help people with coding, um, and get teams set up. I know it's been crazy with finals this past week and everything. Um, so we've been giving grace to people with that because we know it is a busy time. So, but we're here to help, and we don't want anyone to feel stressed if they're a little bit behind, you know. Hopefully, in these next couple weeks, people will have a chance to catch up. Um, and we're here to offer support. And, you know, if you need to meet and want to talk about it more, we're here to help as well. So, again, just to remind again about the paper, we're looking at gap junction conductance, and, you know, the lower ones to represent older flies, higher conductance to represent younger flies. Um, and then again, um, seeing how physiological conditions versus anatomical ones change that conductance. So we'll see if we can do that in Brian. Reminder to use this table for when you're setting your parameters in Brian. Also using the notebooks as well. And there's a lot of resources online. You can look at the BRIAN2 documentation. If you just Google that, there will be resources in that if you're wondering how to model a neuron. So we'll be assigning groups soon, so people can work together. Um, After we put out group assignments, if people in your group aren't responding or they don't um, they're not putting in the proper work and everything, we'll change groups accordingly. Um, and then once we get the coding down and get all that finished for the BRIAN2, then we will work on summarizing those findings. If we notice any differences and if everything is the same, we'll want to report that too. So, maybe people can use either Python package as well. That's still useful information. And then hopefully working on getting that published to that journal as well. So now here is the post assessment. Um, and I'll put that link in the chat as well. And yeah, um, it's normal to, we just learned this Python package and for some people coding in general. Um, so you may not feel super comfortable with it yet, but that means you're learning something new and everything. So that's good. That's why we have this program here is to help people to learn how to code. So um, it's exciting that everyone is learning and growing and everything. So it's good to hear. So if you have any questions, um, feel free to reach out to Kiana or I or anyone on the leadership team, and we'll be sure to answer them. And um, thank you for attending today. And if you have any other questions, feel free to let me know. Otherwise, that's it for today. Thank you for attending, and we'll see you next week.